are also known as fins. Fins are basically meant for increasing the heat transfer rate from a surface to a fluid, particularly when the convection heat transfer coefficients, that is H values, are relatively low, that is with the air. For example, if you take the cylinder of internal combustion engines, we find circumferential fins which will increase the heat transfer rate from the surface of the cylinder to the surrounding ambient air. We also find fins around the cylinder of reciprocating air compressors, where cylinder is needed to be cooled, and also over the condenser of a refrigeration plant, where usually the fluid coolant is air, particularly in the domestic refrigerators. So whenever heat transfer rate has to be increased, we provide fins, particularly when the coolant is air. So, alright, fins are meant for increasing or enhancing heat transfer rate by increasing surface area of heat transfer. Example, air-cooled IC engine has circumferential fins. Number 1. This is number 2. Reciprocating air compressors. Number 3. Condenser of refrigeration plant. In all these things, what we find, the coolant here is, the coolant in all these examples is air, with approximately the convection heat transfer coefficient of 25 or 20 watts per meter square Kelvin. Fins are usually preferable or used only when the H values are relatively low. We never find fins when the coolant is water, where the H values are relatively larger or higher. First of all, let us analyze the rectangular fin. Analysis of a rectangular fin. Now consider a rectangular fin of profile area A. The dimensions of the fin are L, Z, and T, where L is the length of fin, Z is width of fin, T is thickness of fin. Now this is the base of fin, or surface temperature of a wall, which is given by base temperature T0. This is wall or surface from which heat is conducted into the fin. This is the fin. Heat is conducted into the fin at the base, and from the surface of the fin it is convected to the surrounding fluid. Let T infinity is equal to fluid temperature. A is the profile area of fin, which is Z into T meter square. Consider a differential element of fin of length dx. Let us indicate that element in the figure. This is the element what we had considered. Let Qx is the heat conducted into the element. Qx plus dx is the heat conducted out of the element. Q convected is the rate of convection heat transfer from the surface of the element to the fluid at a temperature of T infinity. Now I write the things. Qx is heat conducted into the element, which is equal to, from Fourier law, minus Ka dt by dx. Qx plus dx is equal to heat conducted out of the element, which is equal to Qx plus dou by dou x of Qx into dx. Q convected is, from Newton's law of cooling, HA delta T, that is H into P dx into T minus T infinity. What is P here? P is perimeter of fin, which can be given by 2z plus 2t. In fact, when you are writing HA delta T or the Newton's law of cooling, A should be the area of contact between the surface of the element and the fluid, which is nothing but P, that is perimeter of the fin, into dx, that is the length of the fin. P dx shall give the area of contact of the element with the fluid, and T is the temperature of the fin at that element. So, for steady state conditions, writing energy balance equation, that is heat conducted into element should be equal to heat conducted out of element plus the rate of convection heat loss from element to fluid. Because the conditions are steady, the temperature of the fin at that element would not change with respect to time. That is, Qx is equal to Qx plus dx plus Q convected, that is equal to Qx plus dou by dou x of Qx into dx plus Hp dx into T minus T infinity. Qx get cancelled. Substituting Fourier law, Qx is minus Ka dt by dx into dx plus hp dx into t minus t infinity. Let us cancel out dx also. Now, if you rearrange the parameters, we get d square t by dx square minus hp by ka into t minus t infinity is equal to 0. Here t is the function of x. The temperature of the fin along its length would vary. Our job is to calculate what is that temperature distribution along the length of the fin. That is one objective, to calculate t as a function of x, and also how much heat loss is expected through the fin. So these two are the objectives of the derivation. The objectives of our derivation are: number one, to calculate the temperature distribution along the length of the fin, and also to calculate the rate of heat loss through the fin from the surface or the wall with a known boundary condition of T0. What is T0? T0 is the base temperature or the surface temperature of the wall. Now let us change the variable, that is, put t minus t infinity is equal to theta, implies dt by dx is equal to d theta by dx, and d square t by dx square is equal to d square theta by dx square. Substituting these things in the above differential equation, we get d square theta by dx square minus hp by ka into theta is equal to 0. This is the standard form of the differential equation. Whose solution could be given as theta is equal to, the solution of this differential equation is theta is equal to c1 e to the power of minus mx plus c2 into e to the power of mx. This is the solution of this differential equation, where c1 and c2 are constants of integration to be obtained from boundary conditions. One common boundary condition is at x is equal to 0 implies T is equal to T0, that is base temperature or wall temperature, and theta is equal to theta naught is equal to T naught minus T infinity. This is one boundary condition. The other boundary conditions depends on physical situation. There are three different cases, in fact, that will arise here. Case 1, to evaluate the other boundary condition, there are three different situations or cases will arise. Case 1, the fin is very long and the temperature of fin at the end is essentially that of surrounding fluid. Case 2. The end of fin is insulated so that dt by dx is equal to 0 at x is equal to L. Case 3. The fin is of finite length and loses heat by convection from its end. So for case 1, boundary conditions are at x is equal to 0 implies theta is equal to theta naught, at x is equal to infinity implies theta is equal to 0. So hence the solution is theta by theta naught is equal to t minus t infinity by t naught minus t infinity is equal to e to the power of minus mx. And the rate of heat transfer through fin in such case Q is equal to square root of hpKa into theta naught, that is square root of hpKa into T naught minus T infinity. This is the rate of heat transfer through the fin for the case 1, that is fin is very long. For case 2, fin is finite in length. The boundary conditions are, for case 2, fin tip is insulated. At x is, the boundary conditions are at x is equal to 0, theta is equal to theta naught, that is t naught minus t infinity. At x is equal to L, d theta by dx, this is 0 because dt by dx is 0 at x is equal to L because fin tip is insulated. In such case, the solution is theta by theta naught is equal to cos h m into L minus x divided by cos h ml. Here please note that h is the hyperbolic cos. Cos h means it is hyperbolic cos. So we got the solution to calculate temperature at any x. For this case 2 also. Now the rate of heat transfer through fin for the second case 2 is given by square root of hpKa into theta naught tan hml, that is square root of hpKa into t naught minus t infinity into hyperbolic tan ml, so many watts. This is the rate of heat transfer for the case 2, that is insulated tip case. Case 3 is somewhat much more complicated as such, but we will be writing algebraic situation for the case 2 also, for case 3 also, I'm sorry, that is fin is finite in length and loses heat by convection from its tip. In such case, solution is theta by theta naught is equal to t minus t infinity divided by t naught minus t infinity is equal to cos h m l minus x plus h by mk into sin h m l minus x divided by cos h m l plus h by mk into sin h m l. And the rate of heat transfer is given by HPKA into T naught minus T infinity into sin HML plus H by MK into cos HML divided by cos HML plus H by MK into sin HML. In fact, because the solutions for the case 3 are much more algebraically complicated, there is a slightly shortcut method for the case 3. When the fin is finite in length and loses heat by convection, it could be reduced to the case 2 by increasing the length of the fin through corrected length. That is, the solutions to case 3 could be reduced to solutions of case 2 if length of fin in case 3 is replaced by LC is equal to L plus T by 2. Then whatever the solutions obtained for case 2, they would become the solutions of case 3 also. That means case 3 solutions could be reduced to the case 2 because case 2 is fins insulated tip case by replacing L in case 3 with the LC, that is L plus T by 2. So the case 3 also becomes now simple. Now let me define what is fin efficiency. It is defined as actual heat transferred divided by heat which would be transferred if entire fin area were at base temperature. That is, for insulated tip case, efficiency of the fin is given as square root of HPKA into theta naught into tan HML divided by, if the entire fin is at the base temperature, that is when the fin material has got infinite thermal conductivity, the heat that would be transferred through the fin is given as HP into L into theta naught. So it becomes tan HML by ML. This is the formula for efficiency of the fin for the case 2, that is insulated tip case. This case is very important. Insulated tip case is the most important among all the 3 cases. Now let me define another parameter called fin effectiveness. Effectiveness of the fin is defined as Q with fin divided by Q without fin. That is efficiency of the fin into area of the fin into H into theta naught divided by H into area of the base into theta naught. For insulated tip case, this effectiveness of the fin would become tan HML divided by root of HA by KP. This is the formula for effectiveness of the fin if the fin tip is insulated. Now I shall do a small problem on fin. The problem is given like this. An aluminium fin, thermal conductivity K is equal to 200 watts per meter degree centigrade, 3 mm thick, and 7.5 centimeters long, protrudes from a wall the base is maintained at 300 degrees centigrade and the ambient temperature is 50 degrees centigrade with H is equal to 10 watts per meter square degree centigrade. Calculate the heat loss from the fin per unit depth of material. Because nothing is mentioned regarding the case whether fin is very long or fin is tip is insulated, we have to consider the case 3, that is fin is finite in length and loses heat by convection from its tip. Therefore I have to make a correction in the length. LC is equal to L plus T by 2, that is 7.5 plus 0.15, that results in 7.65 centimeters, that is the corrected length. M is square root of HP by KA, that would be obtained as 5.774 because P is equal to 2Z plus 2T, that is approximately can be taken as square root of M should be approximately taken as square root of 2H by KT. So M is obtained as 5.774. Therefore Q is equal to tan H M LC square root of HP KA into theta naught. where A is equal to Z into T, that is 1 into 3 into 10 power minus 3 meter square, 3 into 10 power minus 3 meter square for 1 meter depth. He has very clearly given, that is Z is taken as 1 meter. Therefore, Q is equal to 5.774 into 200 into 3 into 10 power minus 3 into 300 minus 50 into tan H 5.774 into length is 0.076, corrected length. You will get 359 watts per meter. This is the rate of heat transfer through fin.